I just want to say that I swear, I don't always wear this like physics shirt. I spent I was during the afternoon. I spent like an hour or so just like skating in like 90 degrees weather. Like it, I was just drenched in sweat. So I just had to hop in the shower, and I just wore this shirt because I was just like I don't know. So I don't always wear this. But anyways, we're gonna talk about directional derivatives. So the idea of a partial derivative was this idea of like with a surface, there are many different ways to kind of travel your function, right? We saw that in limits. To find a limit of a 3D function, there's like an infinite amount of paths you can take your limit in, like, there's many different paths that you can reach a certain point on a surface. And it's the same thing for a derivative, right? Or, yeah, like for, or I guess it's like the same thing when you think about a 3D function, when you're thinking about a surface, is like, I guess I should draw one out to show this, but if you have your function, all right, whatever it may be, and I can draw a little grid too. Your, the rate of change, the rate at which your function changes, right? The rate at which that height, that z value changes, it it differs from if you're like you do like a point like right here, right? You could see if you're going in this path or this path or this path or this path, the rate at which your function changes is different depending on which path you take. And with partial derivatives, the most simple case was just looking at, hey, what if you go in the x direction and the y direction? How does my function change? And we call this a partial derivative, right? We called it a partial derivative. And if you think about it, it makes sense because a partial derivative only tells you a part of the story in terms of how this function is changing. If I'm traveling in the x direction, you can see that, well, I guess not in this case, but maybe in the x direction, your partial derivative is negative. So that would suggest that, my function is decreasing as I go along the x direction. But if I go in, that's only part of the story. That doesn't mean the function is always decreasing. As soon as I go in the y direction, perhaps maybe the partial derivative is positive, meaning my function is increasing. So it only tells us a part of the story. And in reality, you can go an infinite amount of directions and see how your function changes. And we call this a directional derivative. So let's say we want to find the rate at which my function f changes. We can just call this f if we go in the direction of a unit vector u. Okay? So the way we write this, the notation will look like the d of u, right? So we use d for kind of like directional derivative of f of xy. So xy at a certain point is going to equal, and the formal definition, right, is going to look something like this. So it's going to look like the limit as h approaches 0 for f. So this is our function, right? Note that u is going to be a unit vector, so that's why I wrote u. And it's going to have, let's say it has components a and b, right? So really, we're looking at the limit as we're going from x, so we'll say x plus ha. So I'm going to just write this down, and we're going to explain why this makes sense. ha, this is, and then comma y plus hb, and then minus fxy over h. So this is really like a pretty traditional limit definition. The interesting thing going on is like this x plus a h a y h b business, right? If you think about, let's say this is our kind of y-x plane, so we're looking at the xy plane here, and let's just say we're at this point xy, and we want to find the directional derivative for something at in the direction of u, right? And just to give you an idea for what this looks like, if this was my vector u right here, right? This is not in the, you can see this is not in the x or y direction. It's like some arbitrary like direction with components a, b. Really, it would actually be on the ground, right? This would be well, it wouldn't have to be on the ground, but there's no z component. This is a 2D vector, so it would just be, you can think of it in the y-x plane, right? There's no height to it. It's not angled up or down. There's no z component. So really, this would be like if we were to take a plane that is like kind of directed in that direction, and then it's going to intersect with the surface, and it's going to have like a little curve, right? And then the directional derivative is a slope along that curve. So, if you remember, the whole idea of a derivative is this idea of like kind of how does a small change in for a partial derivative, how does a small change in x result in a change in my function, right? As we keep making those small changes in x smaller and smaller, the changes in z are going to end up being smaller and smaller, but you end up getting this ratio, partial z over partial x. And this ends up being the partial derivative, right? How quickly my function changes as I'm moving along the x-axis. And in the directional derivative, it's the same idea, but it's like small nudges along the u-axis, or not u-axis, but small nudges along the direction of u. And that's what the h is for. We're saying x plus ha because as h approaches 0, those small nudges are going to be smaller and smaller. However, you can imagine if a is a larger component than b, right? That would just mean that, I forgot to write an x here, but if, let's say in the case that a is much larger than b, you can see that the direction would be closer to the x-axis, right? So, it's sort of like, let's say u is equal to, I got this from a blue, I forgot his name, 3 brown, blue 1. I should know his name because he's kind of a legend. But it's kind of like you're going 2 nudges to the right and then 1 nudge up, right? You're going 2 very small spaces to the right and then 1 small space up. So, that ends up, this is actually not a good example. U has to be a unit vector. I totally forgot. I know I said that. It has to be a unit vector, so this would really be more like 2 over root 5, 1 over root 5. But you get the idea, right? If, one component is much larger than the other, that gives us a direction, but it's, what was my point? What was my point with going on about this? I guess what I'm trying to set this up is for another way, this is the formal definition, but really the directional derivative is going to look like this. Partial f partial x times a plus partial f partial y times b. So, the whole idea being that, hey, if your a component is larger, it's like your derivative is mostly going to be oriented in the x direction. And because you're having more nudges along the x direction, right? You're having more change in x versus b, you're going to have, if your b component is really small, you're going to have less change in y. So this is actually the equation you should know, right? This is what, you can actually prove this using chain rule. I won't go into that, but hopefully this kind of makes sense. It's like, if your a component of your unit vector is much larger for your directional derivative, then it's going to be, it's going to be a larger part of the directional derivative is going to be oriented in the partial derivative in the x direction, right? Hopefully that kind of makes sense. It's honestly, it's one of those things that makes sense in my head, but it's kind of hard to explain. But I hope, you do kind of get an intuitive idea for this. So let's talk about the idea of a gradient. So a gradient is a pretty interesting operation. It is an operation. We use this letter, which is, I know it's Greek and I just don't know what it means, but we use the upside down triangle. And we say that the del f, the gradient of f, we say like del f, del for this. It's not delta though, it's like nabla, I don't know, something like that. Del f ends up being, if you were to take f and you were to take the gradient of f, it ends up being a vector of partial f, partial x as the x component, partial f, partial y as a y component, and then so on, right? So if this is a 3D function, you would have partial f, partial z, right? Or sorry, if this is a function of 3 variables, right? Like f of x, y, z equals, then you would have the partial f, partial z. But if it's just an f of x, y, you would just have this. And the reason this is kind of kind of a good thing to define is because you notice that, hey, if these are the components of a vector, and we know u, this is a unit vector AB, right? That is also like that is also a vector. Well, it looks like we're taking the dot product of the gradient f and u, and that's exactly what we're doing. Actually, we're taking, so we're saying, so du, another way to define this, of f ends up being the gradient f dot u. And this is why it's kind of useful to define this. It's useful to define the gradient because we can kind of express it in terms of dot product. And expressing it in terms of a dot product is also useful because, and also, so keep in mind, the gradient is like a vector, right? And actually, I guess I should show this first. Let's say, let me ask you a question. And I do, if you've never dealt with the gradient vector, I do want you to pause and actually think about it. If on our function, we know we can go in the x, y, whatever direction, right? Any unit vector, right? We can go in the unit vector 2 over root 5, 1 over root 5. We can go any direction we want, so long as it's continuous for that direction. Whatever, we can go in any direction we want. Which direction of f, could give us the greatest, could give us the greatest directional derivative, right? Meaning, let's do an example. Let's say f of x, let's say it's equal to, let's just say it's equal to y arctan, like x to the y. Why not? Oh no, that's kind of nasty. Is it kind of nasty? I guess it's not that kind of nasty. Sure, whatever. We'll do f of x equals y arctan x to the y. Which direction would give us the largest directional derivative? Pause and think about it, right? So which unit vector, let me say this again. Which unit vector would I have to travel in order for it to be the largest derivative possible? Hopefully you've paused and you've thought about it. Let's give it some thought, okay? We know that with this dot product definition, this also ends up being the same thing as partial f, the magnitude of partial f times the magnitude of u times cosine theta. This is just dot product theorem you probably learned in your first few days of Calc 3. Here's the deal. For this function of x, y, how do I, let's see, what's a good way to explain this? What is a good way to explain this? Sorry, give me a second here. I just want to think about what's a good way to explain why what I'm about to show makes sense. I guess we should just go with, I guess this is just how I'm going to explain it. I guess maybe I'll pose a question and I have to think about it some more. But the idea is, well, hey, this will be the largest, right, when cosine theta is the largest. This, right, cosine theta has a range from, well, it really has a range from -1 to 1. But the gradient vector and the unit vector you want to travel in it won't be more than 90 degrees. So we could say it's from 0 to 1, right? So obviously it's going to be 1 when cosine, theta is 0, when they're along the same direction. And the magnitude of u is always 1. So the largest that the directional derivative will be is just the magnitude of partial f. Or sorry, del f. It's going to be the largest of the gradient. So if we were to find this, obviously this tells us that this would be the size of the directional derivative, or the size, like, the actual directional derivative is the magnitude of del f, and the direction would just be, it would just be the same as if I were to do partial f over the magnitude of partial f, and this gives us the unit vector with that, derivative. So let's say we want to, I'll think of a point in a second of where I want to do this, but just to find the gradient, I would end up doing partial f, partial x, right? If I want to find the gradient, I need both partial f, partial x, and partial f, partial y. So this would end up being, so I'm going to do, so this y is a constant, and then I'm doing arctan is going to end up being x, so it's going to end up being 1 over 1 plus x to the y squared, which I think is just x to the 2y, right, from properties, x to the 2y, and then multiply by, we do chain rule, right? So, y in this case is kind of like an exponent, so this is like x squared, right? You just use power rule, so I do y times x to the y minus 1, which honestly is kind of nasty, but I get y squared times x to the y minus 1 all over 1 plus x to the 2y. So this is partial f, partial x, and then partial f, partial y is going to be a little slightly more trickier. Oh, why did I choose? This is a terrible choice. Okay, it's fine. We're going to roll with it. I'm going to do product rule. So I'm going to do derivative of y times arctan. So derivative of y with respect to y is just 1. So I just get arctan x to the y. And then I'm going to do plus, and then y, and then the derivative of arctan x to the y with respect to y. So it's going to be the same thing-ish, 1 over 1 plus x to the 2y. But for the chain rule, it now ends up being x to the y ln x. Because this is now, like, this is like taking the derivative of 2 to the x, where x is a constant. Or 2 to the x, right? But now it's with respect to y, so it's like if x is the constant, so x to the y instead of 2 to the y. This is kind of nasty in all honesty, but I could find, I could find the magnitude if I had a calculator. If I said, let's say I want to find the gradient at x equals 5, y equals 10 or whatever, I could use a calculator, and what I would do is I would plug in just 5 and y, and that would give me some sort of vector. And then I just need to find the magnitude, right? So to find the magnitude, so magnitude of f would just end up being square root partial f partial x squared plus partial f partial y squared. And I would find the magnitude, and then I could find the direction by dividing the original vector. So honestly, kind of nasty problem, but hopefully you get the idea of, an idea of the gradient and the vector. Now, here's the thing about the vector. I've been talking a lot about how to calculate the vector, or the gradient vector, but what does it really look like in practice? Well, like, what does the vector kind of tell us? Well, what does it geometrically look like? I think that's what I'm trying to say. Here, I'll show you. If I had a contour map, so let's say this is a contour map of anything, right? Just any function I want. Oh, wow, it's pretty steep here. What the gradient vector tells me is the direction of quickest ascent, or steepest ascent. We showed that the gradient is, and And I say we showed because I think I was missing something. When I was doing my magnitude of del f, magnitude of u cosine theta, it was like, well, cosine theta can change between 0 and 1. Okay, never mind. My way was good because the angle that you change won't change partial. Okay. We're good. Partial or del f, the magnitude of del f depends on the point, which would be a constant, and then so the vector direction, like, you know, it won't. Don't worry about it. Honestly, don't worry. I'm just confusing myself, and I'm probably confusing you. Anyway, we showed that the directional derivative, the directional derivative of f of x and y, it would be the largest when the direction is the same as the gradient direction. So what that tells us is that, hey, the gradient vector, right? Remember, this is really an xy plane because this is an xy vector. It would give us the direction of quickest approach. So right here, you could see it's going to be like so. And it would be like so here. And then it would be kind of like so here. And you might be saying, how am I figuring this out, right? How am I just drawing in the gradient vector at each point? Well, here's the deal. And also, yeah, okay, this makes sense. How am I figuring this out, right? How is this, then let's give this number. So this is like 500, 300, 100, or whatever. So, there's not really a formal proof for this, but hopefully this will make sense. If we had a vector that was kind of parallel to if you had a vector that was tangent to the curve, then moving along that vector at every point, you would just stay on the curve. You know what I mean? If you go on a vector tangent and then tangent and then tangent and tangent, you would just stay along the same curve, the same height. So that would make you think that things that are tangent have no change in z. Well, this directional derivative, this gradient, is the direction of steepest slope, right? Where the directional derivative is the largest. So the opposite of tangent, which would lead to no change, would have to be normal. The vector is always normal. It's always normal to the curve because it's like the opposite, because it has the most change versus no change. I'm sure you can prove this. I don't know the proof, honestly. I'm actually probably going to read up after this. But you would see that then you can kind of get the distance of, or you can get the curve of quickest or steepest ascent by using along this line would be the gradient, which I think is pretty cool. If you think about equipotential lines in physics, right? Really, the electric field is actually just a gradient, either the negative gradient of potential. And that's why the electric field line is always perpendicular to the equipotential line, which is a pretty cool application. So this has been directional derivatives. I know this video is actually really scatterbrained, and because honestly, I think skating might have fried my brain. But yeah, thank you for watching.